I've noticed that over the years, the internet and my classrooms tend to be riddled with the same questions about stats, year in and year out. So I figured that they're probably worth making a video about. So without further ado, here's my 2 cents on some of the most frequently asked questions about stats, Student Edition. I'll give you the first 2 for the price of 1. What is data science, and who are data scientists? It used to be the hottest job on the market when it first came out, but now I feel like it's more like teenage sex. Everyone talks about it, nobody really knows how to do it, but everyone thinks everyone else is doing it, so everyone claims they're doing it too. One of my favorite descriptions of a data scientist is that it's sort of a person who's better at statistics than any software engineer, but also better at software engineering than any statistician. A data scientist is typically somebody who combines content knowledge, data expertise, but can also execute some methods. They lie in that dicey middle ground where the rubber meets the road and things get done. They're kind of like Liam Neeson in that movie Taken, combining a very particular set of skills, often but not always including some computer programming on the side. There's also some really nice visuals online that I think help paint the picture of what data science is. If you take domain knowledge and throw a little bit of math and stats at it, you get traditional research, whether it's academic or industry. But if you take computer science and add a little bit of math and statistics, then you get machine learning. And if you take computer science and combine it with a little domain knowledge, you get software development. But you put all of them in a bin together, and you get the love child that is data science. Unfortunately, I feel like it's been overused, and now it's too broad to be useful anymore. Sort of like a milquetoast buzzword that you throw on your resume or CV in hopes to get a better job. I mean, business analysts who run regressions and t-tests are now calling themselves data scientists. So really, what are we doing here? What's the central limit theorem, and why is it important? For being one of the biggest cornerstones in all of statistics, this one gets misconstrued too often. And maybe it's just me, but I always feel like explanations of the central limit theorem don't sufficiently emphasize that it says nothing about any one single sample, but instead about the thought experiment of plotting a slew of samples. Or in other words, what certain sampling distributions look like. This deserves its own video, and I'm currently working on it. But in the meantime, here's the big picture. Suppose you want to know how many people like chocolate in the US. So you call up one random person and you ask, do you like chocolate? If they say yes, your best guess at the number of people who like chocolate is 100%. And if they say no, your best guess is 0%. Yeah, they're bad guesses because you're only asking one person, but it's your best guess at the moment. So you try calling a second random person, then a third, then a fourth, and you eventually get 100 chocoholics after calling 500 people. So you finish your poll by saying, okay, according to our sample, 20% of people like chocolate. Now if you do another sample of 500 people, you would expect to get a different result just by pure chance. I mean, if you're calling people at random, you're not going to get the same 500 people. So instead of maybe 20%, this time you get 39% of people that like chocolate. Regardless, you repeat this poll many times, calling 500 people every time. And this is exactly the point that isn't emphasized enough when talking about the central limit theorem. If you're calling a large number of people, the answers people are given are independent of each other, and you perform a large number of polls, along with some other technical conditions that are usually satisfied, the central limit theorem tells you how the results of the polls will be distributed. It says that the results of the 500-person polls will form a bell curve, and in the middle of the bell curve will be the actual number of people who like chocolate.
How neat is that? That's pretty neat.
Why is this important? A lot of methods require strict assumptions that don't always hold in practice. While on the other hand, the central limit theorem requires virtually zero knowledge about the distribution of the population itself. So it lowers the barrier of entry for making better predictions about the population. A slew of inferential techniques like confidence intervals and t-tests utilize this theorem like gas in a car. This one hits right at the heart of science, which normally answers questions in research by testing them as hypotheses. A hypothesis is just a claim, something we don't know the truth about, like men are generally taller than women. If we knew the height of all men and all women, we could easily answer the question, but collecting that data is surprisingly expensive, so it's easier and cheaper to just collect a smaller sample. One problem with this is the possibility that our sample might not be representative of the whole population. This is why random sampling is so important. I'll leave a link to my video on random sampling and bias in the description below. There are actually two hypotheses at play in any hypothesis test. Number one, the null hypothesis, which is exactly what null sounds like. It's the hypothesis of a null effect. If you were checking to see if men and women differed in IQ, the null hypothesis would be that they didn't. And number two, the alternate hypothesis. It's the one that describes an effect. If you were checking to see if men and women differed in IQ, the alternate hypothesis would say that they do. A statistically significant result can't prove that a research hypothesis is actually correct. This would imply 100% certainty, and samples vary, so that's just not possible. Because we're extrapolating from a sample, there's always a chance of making an incorrect conclusion regarding whether or not to reject the null hypothesis. And this leads right into the next question. Suppose there's actually no difference in the height of men and women, but that our sample of women happens to just be very short. If we conclude that there's a difference between men and women's heights, we'd be wrong, and this is called a type 1 error. Now suppose that there actually is a difference between men and women's heights, but that we don't find evidence of it. We should reject the null hypothesis, which says there isn't a difference, but since our sample lacks enough evidence against the null, we fail to reject it. We'd be wrong again, but in a different way, and this is called a type 2 error. In both cases, we're actually testing the same hypothesis, that men and women are the same height, and again, we call this the null hypothesis. We do this by drawing up a distribution where men and women's average heights are the same, and measuring how likely it would be to see a sample like ours on that distribution. If the difference in the heights in our sample is large enough, we reject the null hypothesis in favor of the alternate one, that men are taller than women. In wiki language, a type 1 error is the incorrect rejection of a true null hypothesis, a false positive, while a type 2 error is the failure to reject a false null hypothesis, a false negative. In layman's terms, a type 1 error is when you reject the null when you shouldn't, like Frodo rejecting the help of Sam, his loyal friend. While a type 2 error is when you fail to reject the null when you should, like how Frodo listened to Gollum, even though he was a dangerous liar. Making a type 1 error means making changes or using interventions when you shouldn't, which wastes time, money, and resources. While type 2 errors typically lead to the preservation of the status quo, when change is actually needed. In practice, we choose a certain level of type 1 error to deal with and minimize type 2 errors best we can. Why not minimize both, you ask? Because actually it's mathematically impossible to minimize both simultaneously. And this leads right into the last question. This also deserves its own video, so I'll save the mathy details for later, and keep this one short. A p-value is just a probability used in a hypothesis test to determine what's significant and what isn't. In a hypothesis test, we gauge if the sample at hand agrees with the null hypothesis, or provides evidence against it, which means providing evidence for the alternate. A p-value measures how strong the evidence is against the null hypothesis. But here's the confusing bit. Strong evidence against the null actually leads to a small p-value, while a sample that agrees with the null leads to a large p-value. The typical rule of thumb is that p-values smaller than 0.05 imply strong enough evidence to reject the null hypothesis, and p-values larger than 0.05 imply evidence against the null is too weak to reject it. What's so special about 0.05, you ask? Long story short, not a damn thing. It's pretty arbitrary whether you use 0.05, 0.06, or 0.01. But if you're sticking to science, it's important that you choose this before you start a hypothesis test at all. Choosing what is significant after the test is done is like your teacher deciding on what determines an A after the semester is over, leaving their students' grades up to their own biases. If you like this video or would like to hear about other topics, subscribe, hit the like button, and leave a comment.